In the last class, we have discussed about De Morgan's theorem. So the concept we just learned can be extended to expressions involving multiple variables also. So we have seen for two variables. So they are particularly important when designing circuits using NAND gates and NOR gates, which are considered universal gates. So these theorems are extensively used in logic circuit implementation because they allow designers to convert circuits into equivalent forms using different gate combinations. So now let us study function minimization. So this is involution. So x dash the whole dash equal to x. X dash the whole dash equal to x. So this is the functional minimization. Now one of the primary objective in digital design is to reduce the complexity of Boolean expression. Consider the expression a plus ab. By taking a as a common, and we obtain a into 1 plus a, 1 plus b. Since 1 plus b equals 1, the final result is simply a. Notice how a two-term expression has been reduced to a single variable. So this means fewer logic gates are required in the final circuit. So function minimization helps achieve reduced hardware cost, lower power consumption, faster operation, and improved reliability. So let us consider another example. Expression a into a plus b. A into a plus b. Applying the distributive property aa plus ab. Since aa equals a, the expression becomes a plus ab. Again, after applying simplification, a into 1 plus b, which finally gives a. So this example demonstrates how multiple Boolean identities can be applied sequentially. A complex expression often requires several simplification steps before reaching its minimum form. So the more familiar you become with Boolean identities, the faster you can simplify the expressions. So what is the importance of this simplification? So before concluding this simplification, why minimization is less? So this occupies less chip area, less electrical power, generates less heat, less cost to manufacture, and operates with low delay. So try for this. So this is another type of question. So you can also work out this question. These are some more examples, some more De Morgan theorems. So you can work out all these examples to understand more about the Boolean algebra. So now see the example C, a plus a bar b equal to a plus b, right? Let us now apply the Boolean identities we have learned earlier to simplify more complex expressions. So consider a plus a bar b. At first glance it may appear difficult because both a and its complement a prime are present in the same expression. However, Boolean algebra provides a systematic approach. We can rewrite the expression as a plus a bar into a plus b. Using the complement law, a plus a bar equal to 1, therefore 1 into a plus b, which simplifies to a plus b. This result is very important because it shows how a seemingly complicated expression can be reduced significantly. In digital circuit design, this means a fewer logic gates are required instead of implementing multiple logic gates for the original expression. We can directly implement an OR gate between A and B. As designers, our objective is always to reduce hardware complexity while preserving the original behavior of the circuit. Now, for the last example, A into a bar plus b. So using a distributive law, a bar plus ab. From the complement law, a bar equal to 0. Therefore 0 plus ab, which becomes ab. Notice how one entire term disappears during the simplification. So the resulting expression is simply an AND operation between a and b. This reduction demonstrates the power of Boolean identities. So in practical hardware implementation, replacing a larger circuit with a single AND gate can reduce circuit size, power consumption, manufacturing cost, propagation delay. So now we try with this functional minimization example. I will explain, you try it on your own. ABC plus ABC bar plus A bar C. Our goal is to obtain simplified expression. Take the first two terms ABC plus ABC bar. Factor out AB. So we will get AB into C plus C bar. Using the complement law, C plus C bar equal to 1. So AB into 1 equal to AB. So the expression becomes AB plus A bar C. So this is already considerably simple than original form. So observed what happened. Three product terms were reduced to two product terms. This means fewer gates are required for implementation. Engineers regularly perform similar reductions while designing digital systems such as calculators, communication devices, processors, and embedded systems. Now let us work through a classic proof. Given AP plus AB bar, take a common A into B plus B bar. Using complement law, B plus B bar equal to 1. Therefore, A equal to 1. So A into 1, which becomes A. So this result illustrates an important principle. Although the variable B appears in two forms, it affect completely disappear after the simplification. Consequently, the output depends only on A. In hardware terms, what originally looked like a two AND gates and one OR gate and can ultimately replaced by a direct connection from my input A. Such simplifications improve its efficiency significantly. Another one is A plus B into A plus B bar equal to A. We can use a distributive law and you can apply Boolean identity A equal to A, B bar equal to 0. Just note on this and you work out on your own to get the final result. Result also shown. So substituting these values and taking the common A plus A into B bar plus B, applying complement law, B bar plus B equal to 1. So we'll get A plus A into 1, so which becomes A plus A. So finally we'll get A. Another one is AB plus AB bar C equal to AB plus AB. The result is AB plus AC. And we have another expression A plus B into A plus B bar plus C equal to A plus BC. So you try it on yourself. I given a clue of loss, so you can use factor outing concept and distributive property, complement law, and apply these laws. Again use distributing property, you will get AB plus AC. And for second one also you can apply the same laws. So De Morgan's theorem we have discussed. So these are all some examples questions related to De Morgan's theorem. So you can work out on this De Morgan's theorem. So this is a example, worked out example. You can also work out with these examples. So thank you.